So, hello and welcome student to the lecture, and this is course number MA412 linear algebra, and this is lecture number 22, I guess. Yes. Yeah. So now we will start one new idea, and this is called inner product space. Okay. So let us first start with what we mean by inner product, and then obviously we will define it. What is the meaning of inner product space? So definition. We start with the linear space. So let B be a linear space over a field F, which is either real or complex. So we will focus on only these two things. Okay. So for inner product, we only define for either real inner product space or complex. Okay. Suppose we have a field F which is either real or complex, and you have vector space V which is space over this. Then we define a map. So okay, so a map or a function, whatever. So a map. So we write down by these symbols. Okay, from V cos V to F. I should not say R. It can be C also. Okay. So to F is said to be an inner product if it satisfies the following. Satisfies the following properties. Okay. So what are the properties? So the property number one. So for any, okay, so let me write down that x plus y comma z, that is always x comma z plus y comma z is true for all x, y and z belongs to V. Okay. So what does that mean? That means this is additive in first argument, okay, or in first component, whatever. So this kind of additive. Okay. This property number one. Property number two is that if you multiply scalar for any scalar, say C, multiply on the first component, then it is actually same as take the inner product first, then multiply. This is also true for all x, y element of V, and any C belongs to that field F. Field can be real or complex, doesn't matter. Okay. This is property number two, and property number three is very interesting, and that is called important when the space is the vector space is over a complex field, a complex number, and that is called that when you choose inner product of two vectors and take the conjugate, because if the field F is complex number, then the value can take also complex number. So what will the conjugate? The conjugate will be exactly of this form. Okay, it this is the inner product or other way, right? Okay, and this is actually complex conjugate. So this is complex conjugate. Okay. So when the field is real, if it's real, then actually that implies this is symmetric, right? Inner product so is same inner product. But in the case of complex field, it is called conjugate symmetry. It's not symmetric actually, right? And the number 4, the last but not the least, that property tells you that when you do inner product with itself, so these are all vectors, okay, x, y, z. If you take the inner product with itself, that is always positive, okay, and that is true positive if obviously x not equal to 0. And you can easily prove that with this property you can easily prove that for 0 it is 0 actually, okay. And then maybe we will prove it after some time, okay. So whenever you choose a non-zero vectors and they take in a product with itself, that will give you a positive quantity, okay. So if a map satisfy all this property, then this map is called inner product, okay. So yes, inner product, okay. And a space, and let me just write down, and this B with this inner product is called an inner product space. Inner product space. Okay, so if this f is actually real, and then it is called, it means that V inner product space, it is called a real inner product space, okay, real inner product space. Space, or maybe I can say C or C in bracket, okay. So then we call real or complex in bracket. In the case of R, it is called real, otherwise is called complex in a product space. Okay, so this is a definition, and then obviously we need to define, give you lots of examples so that you can see that this kind of space exists actually. So first example, it's called the standard inner product. So let me define, it's the most important, standard inner product on Fn. Okay, so if is the field, and then if you choose Fn, that will be a vector space of dimension n over F, and then you can talk about whether I can define an inner product or not. Okay, so obviously you can define it. In this case, so my V is what? My V is Fn, and I am defining that map. So you're taking F, X, Y, and X is a element of Fn, so you can write down this is kind of n tuples, X1, X2, Xn n tuples. Similarly, Y can be written as Y1, Y1, Y2, and so on, Yn. And then you define this by definition. I'm defining this by xi yi bar. So write down this, and then sum over I to 1 to n. Okay. Now if I define by this, then what happen? Then obviously you can definitely you can easily say that this is inner product. Why? Because these definitions satisfy all the 4 properties. So let me just prove it, all the 4 properties, whether it will satisfy or not. So yeah, so let us start with three vectors. Say x equal to x1, x2, xn, the element of v, which is actually fn. Similarly, y is y1, yn, and your z is z1 to zn. These are all vectors inside v. Okay, and we can choose some scalar also. C belongs to f. Now property 1, what does that set? So you start with x plus y, x plus y comma z, that you will find out that satisfy that additive in first component or not. Okay, and okay, so one more thing I should say that, so this property number 1 and 2, if you club together, that tells you that this is linear in first argument, right? First of component, whatever. So this tells you that linearity in the first component, first whatever, first coordinate. Or rather, not first coordinate, first component, that is better. Okay, and you can easily find out that for the case when f is real number, so this tells you that it is actually symmetric. Third condition tells you. Okay, now comes here. So let me prove that the way we define the standard inner product, that actually define inner product, the map. Okay, but then what does that mean? That means so your x plus y equal this, but what is x plus y? X plus when you add x plus y inside Vn, so this addition is component wise, right? So the factor x plus y has components x1 plus y1, x2 plus y2, xn plus yn, and hence by definition this is has to be xi plus yi, and then zi bar I equal to 1 to n, right? This is by definition. And obviously from this you can easily tells you that this addition, right? So okay, the property of addition tells you that this is actually xi zi bar I equal to 1 to n and plus yi zi bar I equal to 1 to n. Okay, and now the first one is by definition is nothing but inner product of x with z, and second one by definition inner product of y with z, right? So the first property is true. Okay, now to prove the second property, we start with this. We start inner product of c times x and then with y. C is any constant we have chosen, and then and you know that when you multiply by a constant to element of fn, it will be nothing but multiply in each of this coordinate, right? So cx is nothing but the vector whose coordinates are cx1, cx2, cxn, right? And hence so this inner product will be summation c of xi into yi bar. Okay, and obviously the sum over run from 1 to n. And because c is a constant, c can come out, and then you have summation I equal to 1 to n xi yi bar. And by definition, you see that this term is nothing but inner product of xy. So this also satisfies the property number 2. Okay. Now the interesting part is how to prove the property number 3. Okay. Now to prove property number 3, what I need to prove? So 3. So we need to start with inner product of x, y, and then the conjugate. So this will be nothing but by definition xi yi bar I equal to 1 to n and the whole conjugate, right? Okay, so now we need to use a property of complex number that when you take the conjugate of sum of say two elements, then it will be actually sum of the conjugates, right? And this is true for any finite remaining elements. So it doesn't matter. First you take conjugate and then take sum, or first you take sum and then take conjugate. Both are same. Okay, so that tells you that you can write down this is nothing but sum over I equal to 1 to n xi yi bar and whole bar. Okay, that's its property that a plus b bar is nothing but a bar plus b bar, right? This property I am using. Where here we are complex number. Now if you have product of two elements, if you take bar, then it will be product of individual thing, right? So you can write down this is as summation I equal to 1 to n xi bar yi bar and the whole bar. Okay, so this is the property that a b whole bar is nothing but a bar dot b bar. Okay, now if you take complex conjugate twice, it will be the original one, so you can write down this is as I equal to 1 to n, and then this is real one. Now it becomes so the bar cancels and then yi xi bar, right? But this is again by definition yx. Okay, so the property 3 is also true. Okay, now only thing is to remaining to show that the property 4, that whenever you are taking a non-zero vector, so let this x not equal to 0, so non-zero vector in V, and you want to show that this is actually positive. Okay, but this is by definition summation xi bar I equal to 1 to n, but xi bar is nothing but more of this whole square I equal to 1 to n. Now you see that because this non-zero means what? That means there exists some xi which is not equal to 0, right? At least one xi will be there for some I equal to 1 to n, for some I, right? So otherwise, if all the coordinates are 0, then x has to be 0, right? So x is not a 0 vector, means that means one coordinate will be non-zero. And now we come to where, so you choose that coordinate non-zero, and hence this quantity. See, this quantity can be only 0 or positive, it cannot be negative, right? But because of there exists xi which is non-zero, so this is always positive, right? As this there exists xi. Okay, so x equal to how do I write? So let me write down by this as x equal to x1, x2, xn, and there is some xi which is not 0 for some this I belongs to 1 to n. For some I equal to 1 to up to n. Okay, for some I. So this is property 4, which is also true, and thus this map is a inner product on Fn, and this inner product we call the standard inner product. Okay, and also you generally people call this by dot product. Okay, so this is called the standard inner product, and people also people also call this by dot product. So people say that this x dot y is nothing but inner product of x y, which is nothing but the standard inner product xi y bar. Okay, so they call this a dot product of the vectors, dot product. Of the vectors x and y. Okay, this is that terminology. Okay, and whenever we will talk about f or fn, any such field, any such vector space over f, and then we will always, I mean, if it is called standard inner product space, means the inner product will be always the standard inner product. Okay. Okay, so now let me give some other. So there are many such inner product. Maybe and I mean, given inner product, you can always generate inner product by that. So one such is it's multiplied by a positive quantity. For example, suppose B, this is inner product space. So this is inner product space. Okay, suppose, and you choose some quantity r which is positive real number. Okay, and then you can define another inner product as by this symbol xy of, say, maybe inner product of 1. Okay, I mean, this I'm writing inner product 1 to make it is different than that, and then you can define this by the original inner product, and then you can prove that this is also inner product. Okay, this is also an inner product on V. Okay, always true. And obviously, one can ask what happens if r less than 0, or maybe r is 0. See, r is 0 is trivial one, right? So this is not inner product. But if r less than 0, what happens? Then also you can show that it is not true. In fact, the last condition 4 is false. That inner product still is always positive. Is not true when r is negative quantity. Okay. But this is always inner product. It is, you can prove it. This is homework. Okay. So now let me go to the another one example. So if you start with the space of real valued functions or control functions, so let me write down. So my B is C, say 0, 1. What is C0, 1? C0, 1 is the space of real valued continuous functions on the interval 0, 1, close interval 0, 1, okay, which is this is compact interval. Okay, so that theory we learn in function analysis, why compactness is important. Okay, so space of real valued continuous function on this, then you can define obviously this forms a inner product with respect to vector space with respect to addition of these continuous functions and scalar multiplication. Right? Now the question is that can you define inner product on it, and the answer is yes. So you define, you choose two functions f1 and f2, and then define it by integration 0 to 1 f of x, sorry, f1 of x and f2 of x and dx. Okay, so I choose real values, so I don't have to put this conjugate, otherwise I have to put this. Okay, and now you check that again, this forms are inner product. Okay, so this is also so this is an inner product on V. Okay, is also homework. Do it and show that this is actually inner product. Okay. And now the next example is very important. It's called Frobenius inner products are also important. But for that I need to define something called adjoint of a matrix, or something called conjugate transpose. Transpose you know, but conjugate transpose will be defined formally. So let A be a matrix. So maybe something is a belong element of M cross N matrices or the field F, and then we define the adjoint of A. Some people call complex conjugate transpose also. Let me write on that, conjugate transpose. But we will use the term terminology adjoint. Okay, adjoint of A by this A star. Okay, and what is A star? So the element of that the integers of A star would be of this form, where this Aij star are nothing but you take first transpose Aj and then conjugate it. Okay, is that clear? So the entries are how the matrix look like. So you take the conjugate and then take the transpose, or you take the transpose and then you do the complex conjugate. Okay, whatever. And then this matrix is defined by this is called the adjoint of the original matrix. Okay, maybe let me define an example also here. So is let me just do it in example 2 3i 5 plus 2i. Okay, 3i, or maybe 2i 2 minus 5i I, and then maybe whatever. Okay, so okay, let me do it for this also. No problem. So this is actually 2 rows are there, 3 columns, 2 cross 3 matrix. The current answer will be actually 3 cross 2 matrix. So it will be like this, and so the first row will be now first column, and how to define it? So you first take that conjugate. First you take the transpose, so that become there. Now conjugate. What is the conjugate of 2? So it is actually 2. So 2 comes here. Conjugate of 3i is minus 3i. Conjugate of 5, this is 5 minus 2i, right? And similarly, for I is minus I, and this is minus 2i, and then this is 2 plus 3i, and this is nothing but a 3 cross 2 matrix. Okay, so you can define in general. Okay, but the interesting result will come when you have a symmetry, a square matrix, when number of rows and columns are same. Okay, so now with this definition of adjoint matrix, one can define this important example, like example number 4, inner product, and this is called the Frobenius inner product. Okay, Frobenius inner product. Okay, so we define the Frobenius inner product on the space of matrices. Okay, and so what is my space? My space is space of square matrices over the field if can be either real or complex. Okay, and then what we do, we define, we take two matrices A and B, and we define a product by trace of this diagonal. Okay, this is my definition. This for any AB belongs to V. So this is n cross n matrix. Okay. And now, how to define, how to prove that this is probably inner product? This map is actually inner product. So number one property, you can easily say that you start with say A1 plus A2 and then B, and then by definition this is trace of this B star of A1 plus A2. Okay, and you know that this matrix multiplication and addition, they distribute each other, right? So this will be trace of B star of A1 plus B star of A2. Okay. Now again, trace of A plus B equal to trace A plus trace B, so that will gives you that this is trace of B star of A1 plus trace of the matrix, which is B star into A2, right? Now the first one is obviously, you can see that it is nothing but inner product of A1 with B, and second one is inner product of A2 with B, right? So thus this A1 plus A2 comma B, the inner product is nothing but A1 B plus A2 of B, right? Okay. So this is proof property number one. Now property number two is also simple. It's very simple, and is actually in B star of the matrix C, right? Now C is a constant term, okay? And when you multiply C with a trace of any matrix, then what happens? Then this will come out, right? So you can write down this is trace of C comma B star of A, okay? And then this comes out, so C comma trace of B star of A, which is nothing but C comma product of AB. See, I am taking a constant, or maybe if you confused, then you can take alpha maybe. Yeah. So write down alpha, otherwise you may think that C is also matrix. Okay. So this alpha belongs to the field F. Now I don't think you can understand that alpha is not a matrix. Okay. So this is obvious now. The second property. Now the third property is also important. And what is third property? Third property tells you that complex conjugate and that things. So how do you prove it? So you start with the matrix A and B and take the inner product and take this bar, and then by definition what will happen? So it will be trace of B star A whole bar, right? Is that okay? So you are taking first the product of B star into A, and then you are taking the trace. But what is trace? Now let me just use the fact that what do you mean by trace of a matrix? So trace of a matrix is nothing but sum of the diagonals, right? So when you write down sum of the diagonals, so obviously, so what are the diagonal elements in this product of two matrices? That you need to first understand. Okay, so let me just recall this thing. So given a matrix A, so you can define trace of A by this summation. See, I equal to 1 to n, where A is this matrix Aij, right? Now if you have the matrix B, suppose the B matrix Bij, then what will be the B star? So B star will be B star ij, which is nothing but Bji bar. Okay. Now if you multiply these two things, then what happens? For example, multiply B star with A, then how this matrix look like? This B star A, and suppose this is your Cij, then how the Cij look like? Then Cij will be of the form summation um, Bjk bar and then A K. Okay, so let me just go slowly, then you will have no problem. I just missed one line, otherwise you will have difficulty. So you can write down that B star I K and then A K G, right? This is by definition. But B star I K is nothing but what? So B star is I K is nothing but B K I BKI bar, and then obviously I equal to K equal to 1 to n, K equal to 1 to n, and BKI bar and A KJ, right? So this is nothing but your new matrix, that ith row and jth entries. Okay. Now when you plug those things in, so then what will be the trace of Bij? B star A would be the Cii, so both I and J are the same, right? So let me write down here. So this will be so trace of this will be what? So this will be summation over I equal to 1 to n and Cii. Okay. Now let me write down next page. So B this bar will be summation Cii bar I equal to 1 to n, right? But what is Cii? The bar I equal to 1 to n. The Cii are also sum, right? So there is a Ci is also sum, so you can yes. So you put ij equal to I, and then Cii will be what? So 1 minute. So when j equal to I is summation I k equal to 1 to n, summation k equal to 1 to n, and then we'll have bki bar, and then aki, okay, because j equal to I, aki, this bar, and there is a whole bar is there, that is coming from this bar, okay. So now you have double sums here, okay. Now in the double sum you see that so this is sum over ki and I, right? Now because of norm, we can take the norm inside, so I equal to 1 to n and k equal to 1 to n, so this becomes bki into aki bar, right? bki into aki bar, right? So now it's clear that okay, so AKI bar and BKI. So what does that mean? So this means that okay. So one more thing I need to tell you. So this is, I need to show that this is actually this is actually inner product of BA, right? Inner product of BA will be what? So this is okay. This much is okay. Now I will show that this is actually inner product of BA. Now if you want to find out inner product of BA, that will be nothing but your trace of A star of B. Okay. Now trace of A star of B is what? So again by definition, so I am write down what is A star of B. Suppose this is my matrix Dij, and Dij is what? So Dij is nothing but summation of A star I k and then B k j, and k is 1 to n, right? But what is A star I k? So this is nothing but is the A k I bar B k j, k equal to 1 to n, right? But trace of this is nothing but sum of all those dii, right? So in fact, then what is dii? So dii is nothing but summation k equal to 1 to n, and then b ki. So this j will become I now, and then a ki bar, right? So this is your dii, and hence this is nothing but summation dii, right? Summation I equal to 1 to n, and then summation k equal to 1 to n b ki a ki bar, right? Now you see that this is exactly equal to the previous one, b ki a ki bar. See, and that tells you that these two inner product ab whole bar is nothing but same as inner product of ba. Okay, so that proves the condition 3. Okay, so condition 3 is also true, and we just have to prove the last condition, condition 4, which is also true, and let me give the proof. So condition 4, so condition 4 is what? So you start with the same matrix A, and you want to find out what is inner product of A, whether it is positive or not, and I am assuming the A is non-zero matrix. Okay, so A is non-zero matrix, and this is by definition, this is trace of A star of A, right? And trace of A star of A is nothing but the sum over this ith row and jth column of this matrix. Sorry, as I the diagonals, and I is 1 to n. But this is what? This is actually doubles. First of all, the sum is 1 to n here, and then sum is k over 1 to n, and this will gives you that small a star I k, and then a star ki, because j equal to I here. Okay, and this is now by definition sum over I equal to 1 to n, sum over k equal to 1 to n, but this is what? This quantity by definition. Okay, I should not write down the other. You may feel that there is one more symbol, but this is what? This is a star I k is nothing but a ki bar, right? So this is a ki bar, and then a ki. Now, if this complex number something in something bar is nothing but the mod of that square, right? So that tells you that so this sum is nothing but sum over I equal to 1 to n, sum over k equal to 1 to n, mod of a ki whole square, right? Now you see that because A is non-zero matrix, and that means that for some, at least for one entity is non-zero, right? So as A is not equal to 0, at least one ki not equal to 0. 1 ki means the one entry. One entry is not equal to 0. Otherwise, if all the entries is 0, then it is 0 matrix, right? And thus this quantity cannot be 0, right? Its quantity will be positive. Thus, this inner product of A and A, this is positive. Okay, and this proves that this Frobenius map is actually inner product on the system matrices. Okay, so this is the proof actually. Okay. So now, obviously, you can have many other inner product. So maybe one more. Let me just define it. Maybe number 5, and then we go to the properties of inner products. So we can, if we choose my v is that continuous function on uh, complex values. So let me write down. Okay, and I am choosing that this is complex value continuous function. Okay, not real value. Um, yeah. So how do I write? So this is space of complex valued continuous functions on this close interval, maybe 0 to pi. That is better. Okay. Now if I choose this is my space, then I can define inner product as f1 f2 by inner product 0 to 2 pi f1x f2. This is complex conjugate I need because this is complex functions. Okay, and here I need to do something to normalize this, and this factor is multiplied by 1 by p, so that you will understand that this factor is required. Later you will see that why it is important. Okay, and dx. So this is one of the important inner product on space of complex functions. Okay, and there are many other, or maybe I can give for complex also the polynomials. So maybe if my v is that say polynomial over the field of f. Okay, and then what happens? So maybe let me just do it for r, because it is more interesting over r, right? Polynomial over r. Now in this case, what happened? In this case, you can define. I mean, one more thing: the inner product may not be unique, right? So there may be more than one inner product. So in this case, you can define obviously many inner products. So one of those is maybe let me define 2 actually. So this will be one inner product f of x, g of x, dx. So fx dx are polynomials, and then you can define many other. So let me define one more thing, then minus 1 2 plus 1, and then the similar definition fx dx. Now we show that both are inner product. This homework again. We show that both these are inner product on the space of polynomial. So this is a polynomial. Okay, space of polynomials over R. Okay, so these all are inner product. So there are so many. Obviously, there are many ways you can define many inner product. Okay, so maybe I will stop here, and in our next lecture we will define lots of properties of inner products and define other interesting properties also. Okay, so let me stop here. Okay.